Okay, thank you, Sherry. And again, welcome to Urbana, Illinois, by web. It's a beautiful day here, and it is the last of the CREDC seminars for the fall. And I'm pleased to introduce our speaker, who I always love to talk about his name. Those of you that are over 60 will remember another Zbigniew. Brzezinski was his name during the Vietnam crisis.
I'm not over 60, but I know who that is.
You're not over 60. Okay. Well, this is Zbigniew Kowarczyk, which is almost as complicated as Zbigniew Brzezinski, but as many K's and B's, but that's okay. Zbigniew is a research professor of electrical and computer engineering, but he also teaches, so as far as I'm concerned, he's just a regular full-time faculty member. He's also at the Coordinated Science Lab and probably ITI.
Yep.
So that's three major institutions here. His work is in an intersection of computers and power systems, and in this particular case, I'm familiar with this project, and it's a very interesting thing where the leaders of this came out with a way to confuse the hackers, and that's the defense against intrusion, and it's a very interesting project with redundancy to assure system resiliency, and the title is RAINCOAT. So this will protect you from the snow and the rain and hackers. Zbigniew.
Okay, thank you, Steve, for this nice introduction. I never heard something like this, but anyway, this was nice. So welcome everyone to this presentation, and what I'm going to talk about, RAINCOAT, right? I'm not sure what it protects against rain, but you can try maybe. But the work, of course, has been done by this gentleman here, Hui Lin, who graduated in August 31st, 2017 with his PhD, and now he is a faculty in University of Nevada in Reno, right? So he couldn't come here and present, and I hope in the future he will still continue to work with us on in this frame of CREDC, all right? So what we are going to talk about is how do we try to mislead the cyber attackers by using something what I call here randomized network communications in the cyber infrastructure for the grid, all right? So let me go directly to maybe I spend on this side. Right-handed. So about the motivation. So what really drives this project? What I present here is really some sort of from the left to the right timeline of an attack, right? I divided this into three basic stages. When the first one I call penetration, when the attacker is trying to establish a foothold in the control network or system. Then preparation of the attack, when the attacker is trying to understand, let's say in our case, the physical process, which is control, and to decide what should be the attack strategy, right? So the malicious operations which he or she wants to perform. And finally, the last stage, execution, to deliver this malicious payload, all right, in the system. And you can pretty much represent in this way any multi-stage attacks, not only in the context of power grid, but also in the context of other systems. And I use this to point out that there has been work done, including us, on detecting of this kind of malicious activities in the system early on, in the preparation, in the penetration stage, right? So we use, apply a number of security measures such as firewalls, IDSs. We know about all of this. But we know also that these are not perfect methods, and we have, in terms of shortcomings, we can miss some of the attack, we bypass our perimeter protection, and also it is frequently hard to eliminate false positives, right? One example would be frequently in multi-stage attacks. So many of the attacks really, the first stage is to be able to log into the system using, for instance, stolen credentials. So you use valid credential of legitimate user and you log in to the system, and usually at that point, if I see that you did this, it is very hard or almost impossible for me to tell you whether this is a malicious actor or this is a legitimate user of the system, right? So if you raise a flag at that point, in many cases, or most of the cases, you will have a false positives, right? On the other end of this picture, right, we have been doing some work on trying to detect attacks at the time when you try to deliver the payload, right? And in case of power grid, we try to combine knowledge on cyber and physical infrastructure and use this to our advantage to be able to determine that something bad is going on. There are some shortcomings of this method as well. First of all, they may be too intrusive to the system or intrusive and hard to avoid interruptions of normal operations, and in the context of power grid, people frequently don't like it. And difficult to integrate the responses because we have a physical system where we are not always allowed, let's say, if we detect a malicious command, that we can suspend or postpone this command until we know whether this is malicious or not, right? So the system operators usually don't want this kind of intrusion in the normal operation of the system. So anyway, what we wanted to do in this work, particularly, we said, why don't we look here in the preparation stage? Can we do something and try to either detect the presence of potential malicious attackers or confuse them in a way that if they are able to design, even if they are able to design attack strategies, these strategies will not be efficient and will not cause major damage to our system. So this is our motivation, and this is where we are focusing, all right? So so the challenge which we have is to be able to detect attacks in the preparation stage. What I show on this picture is a simplified kind of structure of the grid. We have a control center on the left-hand side or right-hand side, depending how you look at it. Then we have the substations and field sites, right? And what I show here in substation, we have some intelligent devices such as RTUs or HMI, less intelligent devices, which are what I call here end devices, for instance, relays. And they have internal LAN, which is used to connect them. And I also pointed out here, set of switches which allow us to connect, to support this connectivity in the physical system, all right? And between the control center and the substation, we have wide area network. So this is our kind of overarching picture or target system. So if we want to detect attacks in the preparation stage, the problem which we have is that when the attacker is doing this reconnaissance operation, usually he or she will create very little disturbance in the system. They will do smart things in a sense that whatever they need to perform with respect to our system will nicely be blended with the normal activities so that you will not see any major abnormalities when you are using your regular kind of monitoring or whatever you see in during the normal case. And for this, the attackers usually need to monitor the measurements from the system to prepare the attack, right? And they can use either active monitoring or passive monitoring. In case of active monitoring, they may try to use legitimate requests to obtain measurements, so issue some requests or commands to the system, say, give me some measurements, or passively simply monitor the network, intercept the packets, and try to figure out what is the state, what is the topology of the system, combine this with publicly available information, try to decide what they can do to cause the the maximum damage in the system. So this is why detecting this kind of problems in the preparation stage is not easy. And the best example is, for instance, what happened a year or 2 years ago when we had this attack against power system in Ukraine, right? The attackers used spear phishing to get into the system, to establish the foothold, and then they stay in the system for several months, 6 or 8 months, and during this time, they were actively collecting information, probing the system, and designing the attack strategy. And nobody noticed that they are there, right? So they were nicely hiding in the system so that you don't have a clue that they were there until the time when they decided to execute the payload, right? So the attack itself was quick, was fast. However, the preparation took quite a bit of effort. So there is a problem right here. So now let's see what we consider in our threat model, okay? So what do we trust, what we don't trust, all right? So in the control networks, we assume that attackers can penetrate computing devices on any communication path which connect the control center and devices. So it could be in RTUs, HNIs, right? Or if the engineer, let's say, comes to the substation with his own device, could be a laptop, could be even now smartphone or whatever it is, connects to one of the devices, and because the phone or the laptop was already compromised, everything may be compromised. In the control center, we trust the integrity of the state estimation software. You may ask me here, how do you ensure this? I mean, we have some ideas, but let's, for now, bear with this. Let's assume that this is possible, and I think it is. And in substation, we assume that attackers cannot physically access the end devices, the simple sensors. And we assume that you can't physically go to the substation and hammer them down, all right? And we assume that those devices are simple enough or primitive enough that you can't really run any kind of specialized software on those entities. And this is not wrong assumption. Other people also consider this in the past work. Finally, we use the assumption also that the edge switches, what I understand by those are the first switch, the first switch in this, if you go to from the left to the right on this picture, in the control center, and the switch just before you access the field devices. These are the two sets of edge switches. This is what I call edge switch. And we assume that, as you will see later, we assume that those are SDN or software-defined networking enabled switches, all right? And we assume that we trust them, that they are not, as to say, messed up, all right? And we are now studying, actually, what would have happened if we relax this assumption. But here, let's assume that those switches are trustworthy, all right? So these are our assumptions about what we trust, what we don't. And so this is our overarching kind of threat model, right? So what do we propose then to address the problem of detecting an attacker during the preparation stage, all right? So we propose a RAINCOAT, which creates some sort of trap for the attacker, which tries to get into this system and cause problems. So RAINCOAT, what it does in a nutshell is randomize the network communication in the power grid cyber infrastructure to mislead the attacker. And it does two things really, disrupts the attacker and misleads the attacker. Disrupting it means I introduce enough unpredictability in network so that if you as a hacker observe or monitor the network, you get a picture which is not quite real, but you can't determine what is real and what is not, and you end up with assuming that everything what you see is right. And second, because we present to you craft or decoy measurements corresponding to the presumed state of the system, you will use those to design your attack strategies. And because of this, your strategy, even if you are able to execute it, or this particular payload, malicious payload, you will not cause damage to the system, and as a matter of fact, only a little of disturbance. One thing, just one second, okay? One thing which I wanted to emphasize here is that we don't change configuration of the system. When I say randomize, we don't randomize or modify IP addresses. We do not need any changes in the hardware, except we add some software into the network controllers, which is responsible for maintaining or controlling the software-defined networking. Okay, go ahead.
I first want to understand the idea. Let's say that we have a relay which is sending a measurement to a device to BMP3, for example.
Mm-hmm. Yes.
Can I understand that there will be two traffic? One is normal traffic, another one with a distributed traffic in a way just to.
Okay. I think, this is a very good question, but if you can wait another 2 minutes, okay, I'm going to talk about this, okay, all right? And then if you still have questions, please come back, all right?
Okay.
All right. So I think I said everything what we assume, all right? And so this is the idea, all right? So now let's talk a little bit about going into more details and I will try to describe what we really do, what this randomization really means. So here I have a very simple picture of the same kind of system structure. So we have, SCADA system, edge switches, and finally the end devices. And this first box represents the control center. These are, substations, all right? And in between, right, we have a network. So now we assume that as part of the normal functioning operation of the system, control center periodically will ask for measurement data from the sensors. And in our case, is there any pointer here? So on this picture, this square indicates devices from which each square indicates a device from which we want to collect measurements. In our case, we have 6 devices, let's say. So it sends the request, it goes to the end devices, and the rights, and the circles represent the measurements which are produced by the devices and sent back to the control center, right? And the control center, we assume, will do this with certain, let's say, periodically, with, let's say, frequency of 1 to 10 seconds based on, what is specified in this IEEE standard, right? So this is a normal operation, all right? There's 6 devices, I send a request for data acquisition, and then I get the data. And I do this periodically with whatever period I need. So now, let's see how this will look like when we say that we randomize. Okay, as I said, with the communication, all right? So now what we do, we send, again, the control center behaves in the same way, so nothing changed in terms of the behavior of the system. It will generate, again, requests to get measurements from those 6 devices, right? But now, rather than asking all the devices at once for the measurement, we divide this entire request into number of rounds. Each round will ask subset of devices to give me the measurement. And of course, we want to make sure that we get the measurement from all devices, right? This is still the condition which we want to satisfy, right? So we send here, let's say we have these 3 rounds here, we said. This is how we divide our request. And this is done, this randomization, deciding which 4 devices here will be selected, will be done in this edge switch using, the SDN controller, which we augmented with our RAINCOAT software. And then before we really reach the end devices, we do one more step. Out of these 4 devices, now we select a subset to which we will really send the message or the request, and a subset to which we drop the same request. Dropping the request, physically what it means really is that this device is the same as it is not anymore connected to the network. There is no valid route in the flow table in the SDN switch which would allow the system to find the route to this particular device. And of course, the device is, the important thing to notice here, the device is physically, we do not, rip out the wire and disconnect the device. So physically, it is not disconnected. Logically, there is no any more route to this device. It's not accessible, all right? So these devices which do not get actual requests are marked with these gray circles here. This one, which is to here black and orange here, means that this particular device will get the request. And here, this is what is illustrated. These two devices get the request. They respond, these two devices, they respond here, and we have real measurements from devices, and we have two devices which didn't respond to us. So what can we do? We can spoof those measurements, right? But you can say that, okay, if you spoof then a random number, you generate some random number and you put a value there, right, to pretend that this is measurement from the device, then if the attacker sees these measurements, right, and tries to, let's say, use them to run, for instance, state estimator, it will give him a garbage, right, because the state estimator will not converge or whatever. So it will immediately notice that something is not right, and may give up on trying to mess up your system. And you may say, okay, I don't really care. If the attacker gives up, it's good for me, right? He or she will not do any damage to me, right? So it's good that we're able to prevent that thing to happen. However, the attacker may do something else, right? And we may have some more problems. So what we try to do really is not to go this easiest route and spoof the measurements using some sort of random numbers, but we try to generate values which make sense from the point of view of the current state of the system and topology of the system. So it's not a random number which I give for these two measurements, right? I will give something which makes sense in the context of the particular configuration of the grid, which I'm considering or I have at hand, right?
How do you do that, Professor?
We'll talk about this just in a second, all right? So this is the idea, and it is done until all the devices are able to respond. And of course, the control center gets all these measurements, including the spoofed things, and has a knowledge, we assume that it has a knowledge about what is right, what is wrong, can distinguish, and can conduct correct, state estimation or whatever it may be needed to be performed, all right? One important thing is here that if we divide the data acquisition request into multiple rounds, we have to make sure that all of them complete within the time interval, right, which is so that we don't violate real-time constraints imposed on the system, all right? And of course, you have to measure this, you have to be able to determine this, and we study and we try to determine whether this is in practice really possible. And in the results, I will discuss this, all right?
Question.
Yes?
So the controller is inside the control system? So,
you know how that's the end, right? It has the control plane,
right.
And the control plane, the major portion is the SDN controller, right, which is a single entity. And now, these changes which we make, you can do in two ways. You can implement as an independent piece of software running to the same control plane, or you can modify the controller itself. It's open source what we use, so you could modify the code, right? Now in the switches, you will have flow tables, right?
Right.
And you can use this software, right, to be able to modify whatever you need to do in the flow table. That's it, what you do.
My question is the controller supposed to be, the SDN controller also supposed to be something that will not be compromised and is expected to behave?
This is a very good question, all right? We assume that it's not, right? But we follow-up work on this is follow-on part of this activity is that we try to now study what if the controller gets messed up, or the software gets messed up, right? Which is maybe, separately implemented, right? The controller is single point of failure anyway, if you take SDN, right? You have to implement some redundancy whether you do this kind of approach or not, if you want to make sure that you survive failure of the controller, right? Because it is a single entity. If it crashes, you have to restart it, right? So we are trying to see whether, if we add this software, whether if you have the case when you have an attack or a failure, all the components which we added, are you worse as compared with the case when you use regular SDN, or you are better? And this is a very good question. You need to answer this question before you can claim that this works. Or if you see problems, you have to be able to define what are the limitations, what you have, right? Because I'm 100% sure there will be false models or attack vectors which are benign from our point of view, and there will be ones which are maybe, totally detrimental to this approach. And we have to know this, right? You can guess, or we can guess already what it could be, but we want to verify that. So this is a very good question. Here we assume that it's not compromised, all right? Okay, so we implement this with SDN, or the SDN really does randomize the data acquisition request and spoof the measurements on behalf of offline devices. So it's not only selecting the devices to which you talk and to which you drop the messages, but also the same piece of software or the same level you can implement the algorithm which does the spoofing, right? So everything is in one place. And as I said, hardware infrastructure doesn't change. The only changes are in the software or software-defined networking. Okay. So I will talk here about what we can do in the case when the attack model follows implementation of maliciously crafted commands. So it means that attacker is able to generate syntactically various commands. However, they are crafted in a way that they may put the system into insecure state. So this is our attack vector, right? Another type of attack, which we also analyze, I'm not going to talk here about, is injection of false data injection, right? But I will not talk about this here, right? I'm talking only about what we call control-related attacks. When you generate malicious commands, try to induce damage into the system. So this is what I'm going to talk about, okay? And for this to work, to generate, this decoy measurement, as Prosper asked, okay, we need to decide what would be the for instance, power flows of transmission lines, and based on this, determine what would be the spoofed measurements. So we start with something, and I will show you just in a second what we do, and then we refine the values based on the physical model of the system and, the basic laws such as Kirchhoff law. And based on this, we adjust the initial values, determine all the measurements, and this would be what we will present to the attacker, all right? So let's go and illustrate, how we do this, all right? What it means, really, what we do. So let's assume here on this picture, okay? So the objective of the attacker is to use commands to disconnect multiple transmission lines to cause overloading of the line. As I use term, put the system into insecure state, what I mean is that at least one transmission line is overloaded. You may agree with this or not, but this is our definition of what it means that the system is in a secure state. Okay, you can define whatever you think is the right thing for you. And let's assume that we have, set of real measurements from sensors, and here I illustrated that we get, measurements in terms of power. And this, these things, the graphical icons are not that important here. It's not necessary to be a nuclear or whatever. All right, that wanted to illustrate, you know, the case. So we have one generator, 100 megawatts, 5 megawatts, and 10 megawatts. This is a real thing in the system, right? And now what we do to mislead the attacker, we try to generate or change those values in a way that, for instance, the one which generated 100 megawatts will be visible to this measurement, which we present to the attacker will say this guy generates 5 megawatts, this guy 100, and this guy 10, as it was. So this is our initial kind of distortion to the measurements, all right? And of course, this, if you do this in this way, it may be, or it will be always, that you will in some sense violate, or they will not be representative, or they will not correspond, these changes will not correspond to what is the current topology of your system, and what is the current, you know, connectivity in your system. So what we need to do, we need to adjust them in a way that if taking into account the current, you know, topology of the system, in a way that when you run a state estimator, you will get reasonable answer, right? So that, let's say, state estimation will converge, or you will get something what you say, oh, okay, I got all the things which make sense to me in the context of the topology. We assume that the attacker may know the topology of the system. Yeah, this makes sense. But is not able to distinguish that the numbers or the measurements which we presented to him or her are not real ones. Okay? So if he uses this crafted measurement now, that it will generate or create an attack strategy. In our case, it opens breakers or opens transmission lines, for instance, or close, whatever, the right way. And using those measurements, he may be able to do this, but he will not create any damage or overload of any of the transmission line in the system. So I give you numbers, I give you measurements. You grab them, you say, okay, based on the topology which I know, this is, for instance, transmission line with the highest power flow, and this is when I should, let's say, open the breaker, so this has to be distributed across other transmission lines, and I can overload something. And based on these values, you may be able to do this. However, you will never cause the actual overload of the transmission line in the physical system. Okay. So, because we, as I said, if we do this initial kind of adjustment, we will have problems when we run the state estimator. We see that we don't get what we suppose, so we adjust this by, you know, changing them slightly based on the error from the state estimator. And until this error is within certain threshold, below certain threshold, then we iterate until we get the right numbers. And in our case, could be, for instance, that this one is not anymore 5, but it should be 12. This one is not 100, but it's 96. This one remains what it was. So ultimately, after all the adjustments, you will present this to the attacker, and the attacker runs the state estimator. If you run state estimation on this, you will get everything looking okay, right? And we'll use this to now determine what transmission lines to what breakers to open to overload certain transmission lines. An attacker will be convinced that he or she was successful of overloading some of the transmission lines, but in reality, nothing bad happened, all right? Okay, so now a little bit about how we evaluated this, and there are two pieces to this. From the security standpoint, we use a simulation we use math power to simulate power systems and estimate state after a command is executed, right? And we use this to evaluate what is the likelihood that you can be, that the attacker can successfully can be successful. It means is able to overload at least one transmission line in our network. And on the other side, we use a real physical system. So this is to assess the probability of successful attack. And this is physical network, which we created using Genie test batch, right? Where we have entity, one of the computers is used or emulates the control center. All others represent, let's say, devices in substations. And this is a physical system, and the purpose was to measure the actual delays in network communications, which we impose on the system when we run RAINCOAT, and see whether, if we have all of this in place, whether we can, when we divide a single data acquisition request into multiple rounds, can we still meet real-time constraints imposed on the power system, okay? Whether we do not violate those real-time constraints, right? So we use real system, we're generate some traffic. In our case, this is DNP3 traffic. We use DNP3 protocol to communicate between the device or among the devices, and do physical measurements to see whether this approach is feasible in real settings, all right? So while these two entities, the simulator and the physical system, are not tightly coupled in real time, all right, they interact, but in a way that the measurements produced from here could be used as inputs here to generate the traffic, and also whatever the commands are issued here could be applied to the simulator. But it is not, as I said, tightly coupling that you can do this, run the two back to back in real time and do the things, right? So this is how we did the evaluation. And let's go briefly into some of the results. These are the systems from to evaluate the security. We run RAINCOAT in the context of number of systems, starting from 24 buses to 11,153 buses system. And then the attack, which I'm talking here about, evaluate the control-related attack. So we talk about what it means, right? And so we issued a malicious command that disconnects transmission lines, and it could be one transmission line or multiple transmission lines, different combinations of those, and measure the probability of successful attack. As I said, it means that you have at least one transmission line overloaded. And in a nutshell, the result I will give you a little bit more just in a second. With RAINCOAT, the probability of successful attacks, for instance, for this large system, was reduced from 70% to 5%. And I will go into a little bit more details just in a second. And this is lower or smaller than the probability if you come as a naive attacker and you do simply a random attack when you open or close randomly different breakers without any thinking or any knowledge about the system. As I said, we also evaluate this approach in the context of false data injection attacks. I didn't talk about this, but in our case, we show that using this approach, you may compromise the measurements, but when you run the state estimation on those measurements, the error will be very large, and you will never bypass the bad data detection mechanism here. So in our case, at least in our measurements, we never see the case like this. And we have some also theoretical proof for this, including some limitations. Okay? So now let's talk a little bit more about the results. Okay? We consider three types of attack modes, all right? The first one is targeted attack, when the attacker identifies critical or heavy loaded transmission lines and randomly disconnects critical transmission lines. So it's targeting the lines which are the most critical, all right? And hope that this will cause damage into the system. Then approach when we attack, when we have RAINCOAT in place. So here there's no RAINCOAT, all right? Here there is RAINCOAT. When the attacker does the same, identifies critical transmission lines, but based on decoy measurements, and then also randomly disconnect one or more transmission lines. And finally, this naive or baseline random attack, when the attacker has no or very little knowledge about the system, topology, and state, and randomly disconnect transmission lines, right? Yes?
So what is the constraint on the attacker to not go through all the transmission lines? Like what is stopping him or her?
I mean, if you go and you try to, first of all, you would need to do a little bit more to be able to open, let's say, all transmission lines, right? And probably it would be very easy to detect also, right? So you want to minimize the visibility, right, of what you are doing to the operator. So if you can do this with opening one transmission line, great. But smaller the number, the better, right? So this is the idea. And also, if you can't open all of them sending, you see, when you use the MP3 protocol, right, you can in one message, right, in one command, you can open multiple breakers. But you can't open all, right? There is I don't know how many, but you can open 2 for sure at the same time. But if you now need to open all of them, you will need to, from the simply network perspective, you will have to send a lot of messages. Right?
So the constraint is detection, fear of detection.
I mean, yeah, but I would definitely detect you, right? Everybody will see if you try to massively, suddenly disturb the system, right? So you want to hide as much as you can and cause damage to the system, all right? Okay. So here you have only one graph for this system, RTS 96, which has 73 buses and 120 transmission lines. And you can see here, on the x-axis, you have number of disconnected transmission lines from 3 to 8. 8 is about 4 or 5% of total, whatever. And this is the probability of successful attack on the y-axis, all right? This orange curve is the targeted attack when there's no RAINCOAT and you have knowledge about the system and you targeted the most critical transmission or heavy loaded transmission lines. And the black one is for the RAINCOAT, right? So we reduce this probability quite a bit, right? And you see we are below this blue line, which is for random attack. So we do even better than in the case when you have a random attack, one random attack in the system, all right? And of course, you see this probability, right, is not 0, right? It is here, about a little bit less, maybe 18 or 16%, right? So in some cases, you still will be able, you will be able successfully to open breakers, right? And you may, cause, as we see here, some of the, you could potentially, cause some lines to be overloaded. But one thing which this approach gives you is that this probability is, is lower and lower, but also whenever you generate an attack and you try to access a device, which in when I do randomization is, we call this offline, so it means I drop all the packets to this device, right, temporarily. Then I know that you're in the system, because legitimate user wouldn't send requests to the device which is offline. So if there is any attempt to send a message to such a device, I know that there is someone who should not be there in the system. So I can flag you out, very early, even when you try to, for instance, acquire some measurements, right? So we didn't measure this, what is the likelihood of this, but you can achieve this objective as well, all right? So in this case, we reduce this probability from 90% to about 20% for the five transmission lines being open. Can we do this, this multiple rounds of acquiring the data, dividing this acquisition of data into multiple rounds without violating the real-time constraints? As I said, we measure this in this network, right, using Genie testbed. And this is the summary. We analyze 6 different configurations, all right, and I will give you hint on this, just a little bit information just in a second. And then we measure the delay of communication caused by both latency between the X switches and SDN controllers, and latency of SDN controllers constructing spook measurements. Because I said that everything, I say SDN controllers, but everything is in, now augmented. We augment the SDN controller to do both the randomization and construction of the spook measurement. All of this takes time, right? So we measure this overhead, together to make sure that really this is in real environment really possible. So here are real, measurements of the delays. This is at 6 different configurations. This number indicates number of switches and number of nodes together, and I can give you more details exactly what each abbreviation means. I don't remember all of them. And you will see that RAINCOAT introduces less than 6% overhead on average, as compared with the SDN, regular kind of operation. We call this forward flow control mechanism. So when you deploy SDN, there will be some overhead, regardless whether you use RAINCOAT or not, because of the nature of the system. But if you add RAINCOAT, you get extra 6% overhead. And in all the cases, the control network still meets the requirements of communication latency, so we never violate the real-time constraints imposed on the system, all right? And you see some cases, these overheads here are very small, but you see here, if you look at this picture for this network of 111, entities, switches plus nodes, you see it's almost double, right? So this is the baseline, and this is with regular SDN, and this is with RAINCOAT. So these two are still very little difference. However, here there is, almost twice. And the reason is that we are running those experiments in the Genie testbed, which is used by many users, right? It's not nodes which we control. We simply, let's say, register those nodes to be used to use them, but other people can use them. Network is also shared, so you may have, congestions. You may have other bottlenecks which we can't predict and we can't control. And probably in real life, you may have frequently something like this, or maybe this is the worst case, we don't know this, but this was the worst case in our study. But in reality, you will have all of this, right? You may not have always isolated networks. But even in this case, we did not violate the real-time constraints for the system, for the, to operate normally, all right? So this is my last slide. Oh, I have one more for future work, but I show you the RAINCOAT, which randomizes the network communication and power grid infrastructure to mislead the attackers, all right? And we achieve this by generating this crafted decoy measurement, which will mislead the adversaries in designing, ineffective attacks. And whatever the attacker generates as the attack strategy or option, right, it will, in case of false data injection attacks, cannot pass the state estimation. And in case of control-related attacks, the probability of successful attacks is significantly, reduced. And as I said, for the future, we want to do first this, what I have here in the bottom of this graph. When I talk about experimental validation of the framework, we want to see, we will create, accidental failures as well as malicious attacks against the SDN infrastructure, which hosts our RAINCOAT algorithms, and see what are the implications. Can we survive? Do we do better? Do we do worse? And if so, why? What are the actual, practical limitation of the approach which we have? And of course, some of the limitations will come from the nature of the SDN itself, and we can, say we don't care about those, but some may come from the fact what we try to do, and we want to know those, and we want to investigate those. And then the longer run perspective is that we would like to create something what I call the Integrated Intrusion Detection Framework for SCADA, where the basis will be open source broad IDS. Okay, we have been doing quite a bit of work in this domain in the past. As part of TCG project, we developed, network analyzer for SCADA protocols, which is part of broad distribution now. So if you go and download the software, you get this for free as well. All right. We have been developing, in the past, fast estimation algorithms for mitigating control-related attacks, and the current work in RAINCOAT. And we think that maybe all of this can fit into some sort of single environment or single piece of software with multiple maybe components which could be used in the context of grid. And of course, we don't know the answers, and hopefully at least some pieces could be used in practice, but this is to be seen, all right? So I will stop here. And if you have any questions, I will be happy to answer. Okay, you got tired. Yes.
Oh, well, the obvious question to me is, if you're going to fool the attackers by injecting all this bad SCADA, aren't you also going to confuse your own operators?
I mean, this is what I'm trying to say, that before anything is sent to the operator, we have, you run state estimator or whatever, this software is aware what we have done, and you can get the right measurements and display the right measurements. I had the same question, I think, when I presented during the review, and the answer was the same. So we make sure that operator sees what it's supposed to see, and nothing else. Before something goes to the operator, I will filter out all the garbage. This is the idea, and this is what we have at the moment. But what are the implications if somebody is able to intercept this? It's another question.
We have a question online.
Yes.
Gael, if you want to go ahead and speak.
Yes, thank you for your presentation. I have a question. How do you know exactly to modify the value of the power such that the deception is effective?
How do you know? Can you repeat the end of your question?
How do you know exactly the value of the power that you are going to assign to each substation to mislead the attacker?
Okay. All right. This is a very good question. So we start with this, some sort of maybe not naive, but very simple idea, right? So I know, based on the measurements, what is the current power flow on each and every transmission line. I know which transmission line, let's say that I choose 2 transmission lines with the, or transmission line with the highest load, and transmission line with the lowest one. And then I switch the values. I mean, this is of course not valid in terms of following, all the power loads in the context of this configuration, but this is how I start. And then I try to adjust those values so when I run my state estimator, I get something meaningful. So this is my starting point. So let's say the transmission line with the highest load now becomes the transmission line with the lowest load, and the other way around, right? So this is how I start. Maybe there is a better algorithm or better way of starting and initiating this entire process of generating the decoy measurement, but this is what we have done. And it seems that it works. Did this answer your question?
Yes, thank you.
Sure. Prosper, do you have a question?
No, that was almost the same question.
Oh, okay, all right. Any other questions?
Any other questions online? Going once, going twice. Told to everybody who wants to go on Thanksgiving vacation.
Hey.
Thank you, Zbigniew.
Thank you.
Thanks.